Here's our equation. We need to find the unique pair of positive integers a and n that satisfy it. This might seem daunting, but by methodically exploring the constraints, we can pinpoint the exact solution. An infinite search space is impossible to check directly. Instead, we'll use number theory to find powerful constraints that dramatically limit the possible values of a. Let's examine this equation using modular arithmetic. We'll look at what happens when we reduce both sides modulo a. When we reduce modulo a, the first term becomes 0 since a to any power is divisible by a. The second term simplifies dramatically. This gives us 0 minus 1 to the power n, which is congruent to 2001 modulo a. Since 1 to any power equals 1, we have negative 1 congruent to 2001 modulo a. Adding 1 to both sides gives us our first crucial constraint. A must divide 2002. This is our first major breakthrough. We've narrowed down a to be one of the divisors of 2002. Let's find the prime factorization of 2002. It equals 2 times 7 times 11 times 13. From this factorization, we can list all 16 divisors of 2002. Our variable a must be one of these values. Now let's apply the same technique, but this time reducing modulo a plus 1. When we reduce modulo a plus 1, the second term becomes 0, and the first term becomes negative 1 to the power n plus 1. This gives us negative 1 to the power, and plus 1 congruent to 2001 modulo a plus 1. The value of negative 1 to the power and plus 1 depends on whether n is odd or even. If n is odd, then n plus 1 is even, so negative 1 raised to an even power equals 1. This means 1 is congruent to 2001 modulo a plus 1, which gives us a plus 1 divides 2000. If n is even, then n plus 1 is odd, so negative 1 raised to an odd power equals negative 1. This means negative 1 is congruent to 2001 modulo a plus 1, which gives us a plus 1 divides 2002. These conditions are extremely restrictive. We've turned an infinite problem into a finite checklist. Now, we systematically check which values from our constraint list actually work. For even n, we need consecutive integers that are both divisors of 2002. Let's systematically check our divisor list for consecutive integers. We find exactly 2 consecutive pairs, 1 and 2, and 13 and 14. This gives us a equals 1 or a equals 13 for even n. For odd n, we need a to divide 2002 and a plus 1 to divide 2000. 2000 factors as 2 to the 5th times 5 cubed. We check each divisor of 2002 to see if its successor divides 2000. We find that a equals 1 works since 2 divides 2000, and a equals 7 works since 8 divides 2000. Combining both cases, our complete list of candidates is a in the set 1, 7, 13. Now, we test each candidate to see which ones actually satisfy our original equation. Testing a equals 1. 1 to the power n plus 1 minus 2 to the power n equals 1 minus 2 to the power n. This expression is always negative for positive n, so it cannot equal the positive value 2001. Testing a equals 7. From our constraint analysis, n must be odd for this case. For n equals 1, 7 squared minus 8 equals 41, which is not 2001. For n equals 3, 7 to the 4th minus 8 cubed equals 1889, still not our target. For n equals 5, the result is 84,881, far exceeding our target. No solution for a equals 7. Finally, testing a equals 13. From our constraints, n must be even. For n equals 2. 13 cubed minus 14. Squared equals 2,197 minus 196, which equals exactly 2001. We have discovered our solution. A equals 13 and n equals 2. Our modular sieve has already proven that if a solution exists, a must be 13 and it must be even. We found one solution. The remaining question is, could another even value of n work for a equals 13? Let's define a function g of n as 13 to the power n plus 1 minus 14 to the power n for even values of n. We already confirmed that g of 2 equals 2001. 4 and equals 4. 13 to the 5th minus 14 to the 4th equals 332,877. This value is vastly larger than our target of 2001. As we can see, the function grows astronomically for larger even values of n. The exponential terms dominate, ensuring no other solutions exist. Therefore, the pair 13, 2 is the unique solution to our equation. Let's summarize our elegant journey through this problem. First, we used modular arithmetic to transform an infinite search into a finite problem, reducing our candidates to just 3 values. Second, systematic testing of these candidates revealed exactly one valid solution. Third, we demonstrated that the exponential growth of the function ensures no other solutions exist. Therefore, through the power of number theory, we have proven that 13 and 2 is the unique solution to our equation. Thanks for watching. If you enjoyed this mathematical journey through number theory and problem solving, please give this video a like and subscribe for more challenging math problems and their elegant solutions. Your support helps us create more content exploring the beauty and power of mathematics.